All right, good morning, everybody. Let's go ahead and get some more participation up on the board. Let's go ahead and take a look here. So we're talking about you are in a 1,600 kilogram car. How much force from the engine would be required to accelerate it at a rate of 4.5 meters per second squared? Go ahead and tell me in the chat, kilograms, is that our unit for force, mass, or acceleration? 1,600, should I be plugging that in for force, mass, or acceleration? What does kilograms mean? Tell me in the chat. Yeah, exactly. So taking a look here, anytime we talk about kilograms, this is actually our mass. All right, so we're going to plug this in for our mass, 1,600, right, 1,600. All right, and then over here, meters per second squared, 4.5 meters per second squared. That's our unit for what? Force or acceleration? No worries, Kaden. This is from before spring break, so that's why we're reviewing. Tell me in the chat, meters per second squared, is that a force or an acceleration? Yeah, so this right here is going to be our acceleration, right? So I would plug that in right here for acceleration, right? It literally says it accelerates at 4.5 meters per second squared. And so we're solving for force, which should make sense because it says how much force. So the force right here is my question mark. All right, so if we multiply those together, go ahead and circle the correct answer on the board. 1,600 times 4.5, what do you get? Circle your answer up on the board. I see Mallory up there. So yeah, if you multiply these together, you should be getting, all right, I know it's a little bit messy, 7,200 newtons or 7,200 newtons. That will be our force that we would need for our engine. Go ahead, give me a smiley or an emoji in the chat box if this review makes sense from our last lesson before spring break. I know it's a while ago, so that's why we're reviewing it right now. This is Newton's second law, F equals ma. So reviewing how to identify what's our mass, what's our acceleration, and what's our force. Great job, everyone. Thank you. All right, I'm going to go ahead and send out the links to the notes for today. Remember, you do need to do your notes during class and actually pass them in order to get your attendance as well. Remember, you can get notes credit at any time, but if you also want attendance, then you need to do it during class and pass it during class. So go ahead, open that up, and then raise your hands. I will be asking for raised hands in just a few slides again. So go ahead and start raising your hands once you do have that open, though.
All right, so just a couple reminders again, everyone. Please do not share personal information during class. Your participation is vital, as we will call on you to raise your hand at least several times during this lesson. And finally, that Class Connect sessions are always recorded for educational purposes. All right, today is day 15 out of 60. We are coming back from spring break. We have a 4-day school week this week, so yay for us. All right, and then Thursday, as always, is going to be a recording day where you'll use the recording to guide you on working on your Unit 2 project for this unit. Speaking of which, let's look at where we are. We are now going to move on today to Newton's third law. So we've covered the first and second, now is the third. And just taking a look at what that specifically entails, it says we will able to define and provide examples of the third law of motion and complete calculations involving the actions and reactions of this law. And hopefully by the end, we should get an 80% or higher on the notes quiz, just to demonstrate that we have mastery over these definitions. All right.
All right, let's get those notes open and ready to go. I already sent those links out. I guess I can send them out again in the chat. And then go ahead and raise your hands. Again, I do need 100% raised hands from everyone. All right, so what I want to know is, what do you observe when you see this water bottle being launched? All right, I'm going to go ahead and grab that GIF for us. Give me one moment. Go ahead and tell me up in the chat, what do you notice is happening here? What do you observe is happening here? Okay, what is moving up though? Right, so I know there's something that's moving up. I see Amari with an answer in the chat. Mallory in the chat. Yeah, so we can see that our bottle specifically is moving up, right? So that is being launched upwards. What do you notice is happening to the water though? So our bottle's going up, but what's happening to the water? Excellent, I see Angelina. Plastic bottles moving up due to the water pushing down. Yeah, so this is interesting here. So in order to make the bottle go up, the water actually needs to go downwards. Smiley faces or emojis in the chat box if you can see that happening up on our screen here. All right, so we're going to be talking about how this is related to our third law of motion. Newton's third law of motion. Excellent. All right, let me go ahead and stop screen sharing here and jump back over to our playlist. So yeah, so what we were able to see here, I'll go ahead and type this up on the board, is we saw that the water bottle, right, water bottle goes up while the water goes down. So it seems like these things are kind of going in opposite directions in order to make this water bottle launch, right? You can see another picture of this here, right? Water bottle's going up while the water is shooting downwards, out downwards. Excellent. So this actually is related to our third law of motion.
The third law of motion, which basically says that for every action, there is an equal and opposite reaction. So if we take a look here at the helpful little diagram off to the right, we can see that there are two kids both on skateboards. And if they have their hands touching and they're pushing against each other, they will go off in opposite directions as shown by the arrows at the bottom. So that's what we mean by this statement. For every action, there's an equal and opposite reaction. That just like with the water and the rocket, if I push off of something, all right, and that something is able to move, then it and me and the other object will move equally in opposite directions. However, if I'm pushing off of something that can't move, like let's say a wall, then I will move, but twice as far or with twice as much force because the wall cannot move. All right, but I'm sure we'll get into calculations like that in a couple slides anyway. But that's the basic concept of it.
Perfect. So let's go ahead and try a couple of these out. So we said every force has an opposing force. Every force is going to have an opposite. For every action, there's an opposite reaction. Now, you might have heard this in like everyday life, but this is actually a physics concept. So what I want you to imagine is you can actually do this right now. If you are in a chair, whether it's rolling or not rolling, if you push forward on your desk, which way does your chair actually want to move? Tell me in the chat box, if you push forward on your desk, which way does your chair actually want to move? Tell me in the chat. Excellent. I see Jalen working. I see Kalina working. Angelina? Yeah, it actually wants to move backwards. Yeah. So this is kind of weird to think about, that as I push forward on something, there's actually a reaction. And so my chair actually wants to go the opposite direction, which is backward, right? Backwards. Now, on the other hand, let's imagine you're standing on a boat or on a platform or on something in water. If you jump to the left off of that boat, then which way do you think the boat will actually move? All right, this is why people often, when they jump off of boats, look really clumsy, because the boat actually moves out from underneath you in which direction? Yeah, it actually goes the opposite way. So absolutely, if you jump to the left, the boat's going to go the other way and it goes to the right. And so then you just end up looking very silly as you try to jump off of a boat. Usually if it's like a light boat, you look very clumsy. You kind of fall straight into the water. Now, on the other hand, let's go ahead and think about if you're in outer space, all right, and you're an astronaut in outer space. Let's say that you throw a rock upwards. Which way do you think that the astronaut will actually begin to drift? The astronaut throws a rock upwards. Think about the opposite, equal and opposite force or action-reaction. Which way will the astronaut begin to drift? Yes, they will actually begin to go downwards. Exactly. They will begin to drift down. All right. So I want to give you another example here. So you can see here, right, that again, as we can see here, if one object goes down, like our fuel from our rocket explodes downwards, this will actually cause a reaction the opposite direction. And so our rocket begins to move upwards. Or this is a fun one if you've ever watched Brooklyn Nine-Nine. Let me go ahead and show you this one up on the board. All right, so if you take a look here, what you can see is that they are using a fire extinguisher and they're blowing the fire extinguisher forwards, and so their chair is actually going in which direction? As they're blowing the fuel from the fire extinguisher forwards, their chair goes which way? Excellent. Yes, again, it goes in the opposite direction, and so they begin to actually move backwards. So again, this is exactly how a rocket works, whether we're looking at our water bottle rocket or at a real rocket, is that it works through actions and reactions. Go ahead and give me a green check or an orange X if you're beginning to feel more and more comfortable with this idea of action-reaction. Green check, orange X. How are we feeling about this? Good, good. Perfect. All right, so you will need to be able to do a couple of these on your own in just a few moments. So again, I want to make sure that we really understand it's going the opposite direction. So this is the answer to number 2. All right, so this was our practice one. In a few, you'll have one that you need to do on your own. So again, if you push forwards, the chair goes backwards. If you jump off left the boat goes right. And if you throw a rock up, the astronaut drifts down. So this is the answer to number 2. Go ahead and raise your hands when you have this saved. You have 30 seconds. Go, go, go for number 2.
A little bit more about the third law of motion. So we know this statement pretty well already, that for every action, there is an equal and opposite reaction to the direction of the force. So just like the example with the boat, right? If you try to jump off a boat, you're going to look a bit foolish because as you push off the boat to jump, like the stick person is, the reaction of the boat to your action is that it's going to move in the opposite way that you're trying to jump. And if it happens in a perfect way, then the forces are going to cancel each other out and you're going to end up in the same place that you were originally standing. So forces come to equal and opposite and parallel pairs. So if I push, like if I'm sitting in a chair with wheels on it and I push away from my desk with like say 2 newtons of force, then I'm going to roll back with that same amount of force. All right. So for number 3, we're going to mark the word parallel. Challenging our knowledge, it says, what direction is opposite and parallel to down? Yes, Angelina. Yes, it is up. Right. So just like a rocket, like with the water bottle rocket, because the water is pushing down, it pushes the body of the rocket up. So up and down. Awesome, everyone. Let's go ahead and move on. All right, this one's going to be a complete on your own practice. So we will be in the Q&A chat if you have any questions, but please do not post any answers in the room chat. So, but this one's going to be matching. So we're going to match the term with the definition. Go ahead and work on that on your own.
All right, so now we're going to go ahead and begin to connect the different laws together. So as we move throughout the rest of the unit, we're going to be connecting all the different laws of motion together. So Newton's second law we reviewed at the start of class, which is that force equals mass times acceleration, or F equals ma. Now remember that mass and acceleration we learned are inversely related. The bigger the mass of something, the less it accelerates. Think about a bowling ball is much harder to accelerate than, for example, a soccer ball. Soccer ball has low mass, and so it accelerates really fast. If I kick a bowling ball, it has barely an acceleration. If I kick a soccer ball, it accelerates very quickly. Smiley faces or emojis in the chat if you remember that from when we last talked about Newton's second law. Newton's second law, if that makes sense. Excellent. All right. Now let's go ahead and actually begin to calculate that and make sure that we really understand it both conceptually as well as mathematically. So we have a 5-kilogram bowling ball and a 1-kilogram soccer ball. They're both kicked with the same force, 20 newtons. So we want to see what would be the acceleration of each ball. How do those accelerations compare? So let's go ahead and take a look here. What force are we kicking the bowling ball with? All right, so let's go ahead and take a look here. What force are we kicking the bowling ball with? Again, they're both kicked with the same force. What is that force? Tell me in the chat. Excellent. I see Cody in the chat. Amari, Lena. Yeah, exactly. So they're both kicked with a force of 20 newtons. Just so you know, it should be a capital N. All right, so 20 newtons. Perfect. So I'll plug that in for our force. And what is the mass of the bowling ball? Again, mass, the units for mass are kilograms. So tell me in the chat, what would be the mass of our bowling ball? Read that question carefully. Don't mix it up with the soccer ball. Perfect. Yeah, exactly, Mallory. Exactly, Angelina. Yes, so taking a look here, this right here is our mass of our bowling ball. So that one is going to be 5 kilograms. Now remember that anytime we have a problem that's set up like this, we actually need to do a little bit of algebra. So I currently have the number 5 being multiplied by the variable I'm solving for, which is acceleration. So in order to get rid of multiplying by 5, I need to do the opposite or inverse function. Tell me in the chat, what's the opposite or inverse of multiplying? What is the opposite or inverse of multiplying? Yeah, dividing. So let's go ahead and divide by this 5, all right, on the right-hand side. But whatever I do to one side of the equal sign, I also need to do where to keep things balanced. Whatever I do to one side, I also need to do where. So this will get rid of it on the right side, but I also need to do this where. Yeah, on both sides. So on the other side as well. So I'm also going to divide by 5 on the other side to keep everything balanced. So what do we finally get on the other side? What is 20 divided by 5? Tell me in the chat. What is 20 divided by 5? Excellent. I see Angelina, Kalina. I see Kamal, Lena. Yes, exactly. 20 divided by 5 would be 4. And remember, units for acceleration, we kind of reviewed them at the start of class, are meters per second squared. Again, that squared is actually a part of the unit. You do not need to actually square the number. So now we've taken a look at the bowling ball's acceleration. Let's go ahead and take a look at the soccer ball now. So soccer ball has the same exact force. So what number should I plug in for force here? Again, we're kicking both balls with the same force and trying to analyze what happens to their accelerations. So tell me in the chat, what number should I plug in for force? If it's the same force. Thank you, Cody. Yeah, using that capital N for newtons. Yeah, so again, we have 20 newtons for our force here. All right, but this time the mass of our soccer ball is much lighter. So take a look back at our question. What was the mass of our soccer ball? What was the mass of our soccer ball? Again, mass is measured in kilograms. Thank you. I see Angelina in the chat. Need more people. What was the mass of our soccer ball this time? Yeah, exactly. This was a 1 kilogram soccer ball, right? We can see that. Oops, sorry. We can see that right here. So this again is our mass, but it's a different mass, right? It's a mass of our soccer ball. So same process here. We want to get rid of this 1 kilogram next to our acceleration. So I need to do the inverse function, which we said was division. So I'm going to divide by 1 over here. And that gets rid of it on the right-hand side. But whatever I do to one side, I also need to do to the other side. So tell me in the chat, what is 20 divided by 1? What is 20 divided by 1? Anything divided by 1 is still itself. So 20 divided by 1 should give me what acceleration? Excellent. I'm seeing the number. Let's go ahead and also tell me what units should I use for acceleration. What units should I also use for acceleration? 20 divided by 1, and then our units as well. Perfect, Cody. Yeah, meters per second. Square that little caret with the number 2. Tell us that second gets squared. Okay? All right, so taking a look here then. Our bowling ball, which is very big, 5 kilograms, that's almost a 10-pound bowling ball, over a 10-pound bowling ball. Its acceleration is only 4 meters per second squared. So compared to the soccer ball, which is much lighter but has an acceleration of 20 meters per second squared, is the bowling ball's acceleration big or small? Tell me in the chat. With its large mass, does the bowling ball accelerate quickly or slowly, big or small? Yeah, we end up with a pretty small acceleration. So if I kick a bowling ball and I use the same power as if I kick a soccer ball, the bowling ball is just not going to move quite as quickly. So our soccer ball with its small mass and 20 meter per second acceleration has a much larger acceleration. Go ahead, give me a smiley face or an emoji in the chat box if this is beginning to make more sense, right? We've talked about it conceptually. Now we can also kind of see it mathematically. All right, so this is going to get into a kind of tricky part here, okay? So don't be too intimidated. We're going to work on it together, okay? So here's the thing. If forces are equal, right, we know they're opposite at this point, but if they're equal, then why don't both objects always experience the same type of motion? So for example, all right, if we have a small 32 kilogram child that jumps to the right off of the boat with an acceleration of 4 meters per second, the boat, which is much bigger at 256 kilogram, barely moves. So the question is, how can this be if we said they have equal forces? Go ahead and give me a yes or a no in the chat box if you understand why I'm asking that question. All right, so again, we said they have equal and opposite forces, but why does the boat barely move? Give me a yes or a no if you understand my question here. Excellent. All right. Well, this has to do with what we literally just took a look at. So let's go ahead and talk a little bit about this. Again, Newton's third law, right here, third law, says that forces are equal and opposite. So the force of our child will be the opposite or negative of the force of our boat. Cool. So that part makes sense. Now we also have Newton's second law, and we said now we're going to be combining them. So we said force is equal to mass times acceleration. So instead of saying force of the child, I can just say mass of the child times acceleration of the child. F equals ma. Okay? Same thing over here. Instead of force of a boat, I can just put negative force, mass of the boat times acceleration of the boat. Go ahead and give me a smiley face or an emoji in the chat box if that makes sense. Again, force is the same as mass times acceleration. So that's why I can substitute these. Smiley faces if that's beginning to make sense. Again, force is mass times acceleration. Thank you. I see Cody in the chat. Kaden in the chat. Beautiful, beautiful. Give me smiley faces. Again, force is the same thing as mass times acceleration. Perfect. All right, so we have some of this information here. So what is the mass of the child? Again, mass is measured in kilograms. Take a look at our question. What is the mass of our child? What should I be plugging in for the mass of the child? Tell me in the chat. Thank you. I see Cody, Mallory, Kalina. Yes, it's 32 kilograms. So this is our mass of our child, MC. So let me go ahead and plug that in. So we have 32 right here. And what was the acceleration of the child? Again, acceleration is meters per second squared. So take a look for the units, meters per second squared, but for the child. Again, we have two objects here, so specifically, what's the acceleration of the child? Thank you, I see Angelina. Again, units for acceleration is meters per second squared. So where do you see that in relation to the child? Yeah, exactly. So you should see 4 meters per second squared right here. So this is our acceleration of the child. So I'm going to go ahead and plug in over here the number 4. All right, so that's what we have so far for the kid. Perfect. Now, on the other hand, we can see, right, on the opposite side, we have the boat. Now, the boat is 256 kilograms. So this right here, is that a mass or an acceleration? M or A? Tell me in the chat box. 256 kilograms, is that a mass or an acceleration of our boat? Yes, this is our mass. So I'm going to go ahead and plug this in as MB, mass of our boat, so 256. Don't forget there is a negative sign because it's going in the opposite direction. So that'll be important in just a moment. And again, we're actually solving for the acceleration of the boat. So let's go ahead and begin to simplify this. So on the left side, I can first actually multiply this. What is 32 times 4? Grab a calculator or do some mental math and tell me what is 32 times 4. This is something that we can definitely easily simplify. We don't have to do any algebra yet. Yes, I see Cody, I see Noah, beautiful. Lena. Yes, yes, yes. Perfect. Yeah, this is going to be 128. So looking at this, we just did mass times acceleration. You actually just calculated the force of the child. All right, so that looks cool. On the other side, we're going to just pull this down, leave it as 256, negative 256. Now again, we need to now do some algebra because we want to get this acceleration of the boat by itself. Oh, no worries, Seraphim. Yeah, double check, maybe you plug something in weird? I don't exactly know how you got 129. So just try it again in the calculator and see if it works, okay? We want to get acceleration of the boat by itself. I'm currently multiplying by negative 256. So if I want to get rid of it, I need to do the inverse or opposite of multiplying. So tell me in the chat, what is the inverse or opposite of multiplying? Yeah, exactly. So we're actually going to divide by this number, which is negative 256. And that gets rid of it on the right side. But whatever I do to one side, I also need to do where? Tell me in the chat box. Whatever I do to one side, I also need to do where? Yes, Mallory, exactly. On the other side. So I'm also going to divide by negative 256 on the other side. So go ahead, grab your calculators. All right, you don't have to put the negative in, just know that your answer should be negative. So 128 divided by 256, and then tell me that in negative. Go ahead and calculate that, 128 divided by 256, and then make it negative. Tell me in the chat, what do you get? Excellent, I see Kalina, I see Carlos. Carlos, those units are so close. You're just missing one thing on that second. Let's go ahead and get some more answers in the chat. All right, waiting on some more participation. Awesome, I see Jonathan. Let's get some more answers. Let's go, let's go. Thank you, Cody. Cody, don't forget the negative. Again, there is actually a negative there. Thank you, Angelina. Yeah, so we should be getting negative 0.5 meters per second squared, all right? Remember that squared is a part of the unit. So all of that being said, you're like, okay, that was a lot of numbers, Miss Larkin. What does that all mean? So here's the deal. Our boat had way more mass. It's 256 kilograms. It's huge compared to the child. And its acceleration, tell me in the chat, did it end up having a small or a large acceleration? Taking a look here, 0.5, right? It's going in the opposite direction. That's why it's negative, right? But 0.5, is that a small or large acceleration? Yeah, this is much, much smaller. Again, so this should make sense. The bigger you are, even if you're experiencing an equal force, the less you accelerate. All right, we saw that with the bowling ball and the soccer ball. Now we're also seeing it in our equal and opposite scenario here, okay? Now the child, which had less mass, right, and an acceleration of 4 meters per second squared, right, is that small or large compared to the boat? Is that small or large compared to the boat? Again, it actually had a 4 meter per second squared acceleration. So comparing that to 0.5, is that small or large? Tell me in the chat, is that small or large? Hello? All right, so 4 meters per second squared compared to 0.5, is that small or large? 4 compared to 0.5. Again, the negative is just saying it's going in the opposite direction, but 4 compared to 0.5. Yeah, this is going to be a large acceleration. So again, the smaller you are, the more you accelerate, even if you have the same force. Smiley faces or emojis in the chat box if that makes sense. Right? So if you have the same forces, but you're big, you don't accelerate as much. If you're small, you accelerate a lot. Awesome. All right, let's go ahead and summarize that. This is number 5. So the answer here is negative 0.5 meters per second squared. Keep in mind that for the units box, you do need to write it as m/s with a caret and a number 2. Otherwise, the computer will mark it as incorrect. All right, so, and don't forget your negative sign for the number. All right, so this is the number, and then this is the unit for number 5. And then again, for number 6, a boat with more mass actually has a small acceleration, and a child with less mass actually has a large acceleration. Please go ahead and answer both number 5 and number 6. I'll go ahead and give you 45 seconds because there are 2 questions. Go, go, go.
Forces are not the same as acceleration. The mass of each object matters. So just like we learned about with the boat and the small child. The more mass an object has, the less acceleration or change in motion it will have. It has. Even with the same equal and opposite force, an object with less mass. So again, the larger the object is, the more mass it has, the more it can resist the change in motion. All right, the smaller an object is, the more it can accelerate and change its motion. All right, let's go ahead and mark for number 7 the word mass.
All right, so finally, let's go ahead and apply this. So if 2 objects experience equal and opposite forces, again, even though their forces are equal, their accelerations will be different. So you want to think about the object with less mass, like a cannonball. Will it have a small or big acceleration? Don't put answers in the chat. And then the object with more mass, like a cannon, will it have a small or big acceleration? Again, think about this in real life. Which one has more motion, right? Think about the cannonball. Will that one have more motion, more acceleration? Or less motion, less acceleration? And then same thing with the actual cannon. More motion, acceleration, or less motion, acceleration. So go ahead and work on question number 8. I'll go ahead and give you 45 seconds. If you want to check your answers, we are in the Q&A chat. Go, go, go.
And reactions and learn how mass and acceleration interact with each other. Go ahead and submit your quiz if you haven't already. All right, go ahead and tell us how well you did so we can shout you out.